powered by AWS. And of course, we have our guest, Anurag, Seth. And of course, this session is powered by AWS. And Anurag Seth is Principal AI and ML Advisor at AWS. Anurag has more than 25 years of experience in technology and entrepreneurship across semiconductor chip design, electronic design automation, building and deploying state-of-art AI ML models and applications across various industries. As the India Design Center head of Kawasaki Microelectronics, Senior R&D Director at Cadence Design and Motorola, now NXP, he has led large product R&D and cross-functional teams with a proven track record of delivering many successful technology products. Additionally, Anurag has also founded an AI-driven health tech company, successfully exited it before serving as a co-partner and CTO in residence at Tembusu ICT Fund, a Singaporean-based deep tech VC. He holds a master's in computer science from BITS Pilani and executive master's in international business from IIT New Delhi. Let me welcome Anurag. Let's have a round of applause and let's learn how AWS can power your AI. Of course, you had seen Microsoft in the morning. Let's see what we have from AWS as well. Thank you.
Thank you so much. You have should I use the?
Yeah, that's okay. You want to use this?
Yeah, I think I'll just.
Okay.
Thank you so much for the introductions. Okay. So thank you so much and appreciate the opportunity to be here today. Before I start, just sort of a little by show of hands, how many people are building anything around generative AI? Oh, very few people. And how many people would say are knowledgeable, or at least they have some interest, some idea about what generative AI is all about? Oh, quite a few. Great. So what I've done essentially in the presentation is that one part of the presentation is about unraveling what generative AI is all about. It's a very malign term. A lot of people are trying to see what they can do. It's like sometimes it's a FOMO in terms of fear of missing out and figuring out use cases for which can fit into it, and reverse engineering it or whatever. But I want to make sure that maybe I'll cover. Is it okay if I do a little bit of basics of that? Some of you are pretty new to it, or should I just jump into little bit more technical jargons about what's the stack on AWS looks like? So do you want, what's the best show of hands? Or do you want me to go through a little bit of it's a 45-minute, it said Masterclass, so that Masterclass would mean I'll try to unravel some of the small, interesting sort of, basics of generative AI. So just show of hands, we'll do that? Okay. So great. So just pace me a little bit, please be interactive. If you think that it's too mundane, too rudimentary, I'll speed up. Just interrupt me in between. If you think it's a little bit more technical jargonish, also please interrupt me. I'll try to pace it the way it suits the audience. Is it okay? Can it be interactive? Thank you. Thank you so much. So let me begin. Of course, oops. How does it go? Cool. So anyways, my introduction has happened. Let me move through it. So it's basically a the AI ML today is going through a inflection point. I mean, and the key drivers, we've been using AI ML very successfully for the last many years. Chandrayaan landed day before yesterday. I think the key success factor was essentially the AI algorithms running on that constrained hardware there. Today we have luxury of GPUs and everything when you do stuff, but Chandrayaan didn't have that, right? So success of AI ML has been powering for a long time. But why is it as an inflection point? Is because of the compute capacity increase, the data, and the size of the models, right? Those are three elements driving what's happening in generative AI. But what is generative AI? Why is it any different from what we've been using as traditional AI, if you allow me to use that word called traditional AI, if there is anything like that. But we've been using it for so long, I mean, at least 10, 15, 20 years. I mean, there have been those, so-called AI winters and resurrections and everything. But even at least the last 10 to 15 years, with all the convolutional neural networks and all this stuff, and CNNs, RNNs, and all the standard jargons which people are using, a lot of good in computer vision problems, a lot of regression problems, a lot of predictive problems have been solved, right? Across the board. But what is so different with generative AI? Any guesses? Human-like conversation. Okay. So great. I think what is different in generative AI, what is happening, is about the machines having the capability today to generate content. And the content could be text, as you say, the human-like speech, could be code, software code, could be images, could be videos, could be audios, could be molecules for drug discovery, could be anything. So we're able to generate that human-like content. That's the reason the whole term generative AI came. We haven't been able to do that before that. Till now, all the traditional AI did was essentially either doing regression problems, the predicting based upon the historical data. You're going to do a weather prediction or a stock prediction or a housing sort of a price predictions and everything, or you're going to do some classification like computer vision problems, right? Here is an object and doing an object recognition. It's a classification problem, right? So that's what we were doing with traditional AI. We'll train the models and they will learn to do that, right? But now we're able to generate, and that's what is actually what has happened, and that's why the term generative AI comes in, right? Now, needless to say, 2022 has been a year of generative AI, and look at the staggering numbers over there. Gartner predicts that the productivity improvements generative AI will usher, it'll be about $7 trillion in the next 10 years. That's humongous, unheard of when it comes to AI impact in the economy. Then, even despite the slowdown on investments, generative AI investments have been soaring, have been sticking on. $3.9 billion, and that's a little tentative number because the data tagging has not been very accurate in terms of who are true generative AI companies versus who are like traditional AI companies. So there's a little bit of a tentativeness of the data, but it's an indicator of how much investment is still going on in generative AI. Not just generative AI core companies, but also in adjacencies. Like the databases, now needed to sort of do some applications around generative AI, like the vector databases of sorts. So there are also investments happening. The projected growth is at about 32% CAGR, which means $98 billion market by 2026. That's humongous. Now, but where did it all start? So if I trace back the history, and again, I'm getting a little technical here, it started with the paper in 2017 called Attention is All You Need. This came in 2017. And what happened in that is two things. One is efficient use of parallel compute. And more importantly, they gave what is called the self-attention, multi-dimensional, it's a little technical, multi-dimensional self-attention mechanism, which allowed the systems to be able to capture the smallest nuance of language semantics. Right? What that means is, for example, if I have a sentence, the food was good, but the service was terrible. Now again, similarly, if I give you some more examples, like I go to a river bank, or I'm walking down the river bank, or I go to the bank to withdraw money, or can I bank on you? Now, the word bank is used in different contexts and different meanings, different semantic connotations there, right? Now, and the context is the words appearing before it and after it, right? So this attention mechanism said if I create an attention for every word, both bidirectional, look ahead and look behind, which means that the word food will have association with the words before it and after it, and I'm able to capture that relationship in a strong or a weak or some numerical number there. Now, if I can do that, now imagine what this can do to you. If I have a corpus of billions and billions of sentences in English language from Wikipedia or whatever, which is capturing the smallest nuance, and if I have a network or whatever, hardware or network or neural network or whatever you want to call it, which is big enough to capture the smallest semantics. Now, that's where interesting things happen. And that's exactly what this paper initiated. But it's been 5 years. So we didn't hear about the ChatGPT or any of these so-called language models, large language models, till about last year. But what happened in 2022? Why suddenly this whole thing about LLMs, large language model, generative AI, only in 2022? Paper came in 2017. And things move very fast, right, in this industry. But what happened in 5 years? Why is it 2022? Any guesses? Well, I come from a semiconductor design background, and in the last 30 or whatever years I've been in job, we have lived what's called the Moore's Law. Anybody knows and heard of a Moore's Law? Can anybody hazard a guess what a Moore's Law is? Sizes. Yes, absolutely. Fantastic. Every 18 months, the size of transistor reduces by half, which means the number of transistors on a single X by X die would double. And the size per transistor goes half. And we have lived this Moore's Law for so many years. When I started career 30-something years ago, we were working on a 1.2 micrometer of a single chip, single transistor. Guess what's the size today? Yes, 2 nanometers. Micrometer and nanometer. And that's what we have lived. And when I do a 2 nanometer semiconductor design, there are oxide layers which we put for an insulation. You know how thick is an oxide layer? 10 I am strong, 2 molecules. That's where we have, every time we feel, hey, we're going to exhaust the Moore's law, something new comes up and we're still able to meet it, right? But what happened in the language world is even more outstanding. We have seen 15,000 times increase in the size of the models. Look at the growth in the last 4 years, from 2022 to 2022, 2 years. The size of these models, size in the sense of number of nodes, number of layers, and number of parameters they sort of represent, have gone up to about almost like 1 trillion. You know, GPTs are like 200 billion or 300 billion and so on and so on. There's a 15,000 time increase in 5 years. We haven't seen anything like that in Moore's law or in semiconductors, right? And that's basically what has happened in the last few years. Even despite the fact that 2017, the paper came out, the attention is all you need. But 2022, when they trained a model of 200 billion parameters, something interesting started to happen. So other piece which this particular paper gave was what's called the transformer architecture. It's a wonderful architecture, and most of your language models which you see are based on this architecture. So there is an encoder which inputs are going into the encoder. Inputs are your words and sequences. You know, I go to river. You know, I like the food or whatever it is. And then you essentially create a two-dimensional lookup. You know, in terms of look forward and look behind. And do create an attention of relationship between words in a sentence, right? You have, of course, an absolute sort of embedding of that particular word itself, but also a relationship with the words appearing before and after it. Now you code that into some kind of what's called the latent space, and you forward that into a decoder. And decoder takes that thing and generates something. It's a forward-looking, it's a one-way, unidirectional thing. It generates, and all it does in decoder is essentially create what is going to be my next word. And what's the probability of next word appearing? And that's basically a very simplistic architecture of a encoder, decoder, or what's called the transformer architecture. Now what that does is allows you to, and this is another thing I want to highlight about decoder, is that it is essentially auto-regressive. Normally what you do in a typical machine learning or AI algorithms is you take data, you label the data, use the data to train your model, right? In this case, the corpus exists. All you're doing is predicting the next word, right? So if I have a corpus of English language, I know what's the next word coming. So that's the reason they call autoregressive, that you don't have to label the data. You have data of English corpus or any other language corpus available, so you know what's the next word, and that's something which you can use to train these networks on. Now there are 3 types of models generally. One is encoder-only models. These models will encode the word sequence into the semantic interpretation. Like you have a word, I love Delhi. Now based upon the attention mechanism which I sort of alluded to, you can now figure out, create a numeric vector representation of semantics which this sentence word represents and which this entire sentence represents. Now you can use these models very well for doing some classification around that. Hey, what's my sentiment of this sentence, right? So that's very good at these encoder models are very good at doing things like this, sentiment analysis. Then they're good at doing it's from a childhood, we were doing this fill in the blanks, right? The masked word. There's a sentence, one word is missing. Can I predict the word? Yes, because I know the semantics, I know the context in which words are appearing, I can predict. So these models are good at predicting some of the masked words or the fill in the blanks there, right? Other models are, decoder models, decoder-only models. These models, this is the typical model which most of you have used. When you see ChatGPT or any other GPT or any other LLM model, most of them are decoder-only models. So when you give it a prompt, it generates, and by the way, the API is available to you today, which allow you to do the question answer using a GPT or these kind of large language models. They are called completion APIs. Why? Because it's only trained on one thing, as I alluded to earlier, next word prediction. So if I start with the word my, it just predicts, okay, next word is name with a 99% probability. Maybe it's a city with a 98.1% probability. And that's what it does. Once my name, what's the next word? What's the next word? And what's the next word? Can you believe it? The entire LLM, these models are trained only on that. If anybody says they understand the meaning of sentence you're giving, or they understand, they understand the question being asked, they interpret they're sentient in nature, my school of thought believes it's not so. They're essentially only doing the next word prediction. That's all they're doing. But yes, they're able to exhibit some interesting behavior, and which you all are privy to, and we'll talk about it why. But they're trained essentially around next word prediction. Make sense? Or is it surprising, or is something which is obvious? But that's basically what it does. Then there are encoder-decoder models. Now you combine encoder and decoder together, in which the input to the decoder is an encoded sort of a latent sort of a representation. They're good at language translations. For example, if I say something in English, I can represent that using an encoder into some sort of a semantics, and then give that to the decoder, which can now translate it to Hindi. So language translations they're very good at. These are called sequence-to-sequence models, or they're called encoder-decoder models, very good at language translations. Now, while that was happening, we were also seeing a lot of improvements in historically in terms of computer vision, where you could sort of describe a text or describe an image, describe a scene, and then say, can we do the opposite? Can we give a text and can it generate the image for us? That's where DALI, stable diffusion, and other technologies came up, which allow you to generate text from image from text. Now, I want to highlight one thing don't go by the little complicated diagram on the left, but I just want to highlight one thing in this diagram, that all these models are probabilistic models. That means they're essentially, when you put a text, it points to some probability function, and using the probability, it generates something randomly. They're very random generators typically, both language side as well as image side. So one thing you can see on the left is a technique used for generating images called variable autoencoders. Now, one of the aspects is when they're training the data, training on a set of images, millions, thousands of millions of images. Now, typically a language model, typically a convolutional network or the other traditional computer vision models would train it to generate something. For example, if I give a cat's image, it should be trained, oh, this is a cat. The output is that this is recognized as a cat, right? But here they're training it on a probability distribution. What do I mean by that? That when you have to generate an image which is n cross n sort of a pixels, now every pixel would have some sort of a gray sort of a scale to that, or a colored scale to that, right? Now, how these variations, how these pixels are varying for a specific image. For example, if I say I want to generate an image of an astronaut riding a horse, that points to probability for distribution, and I randomly sort of pick up the pixel coloration based upon matching the probability distribution to make something or generate something which looks like an astronaut riding a horse. They're all probabilistic models. That's the reason no plagiarism. That means they're literally generating on the fly, randomly, but matching a certain probability function which is learned using training. See what I'm saying? So every time a new image comes out, it's random, a new image, but it matches sort of probability distribution which you have trained using training data. Other techniques like which stability diffusion uses is also called diffusion process, which again is very probabilistic. What you do is you take a set of images, you train the data, train your model to learn certain noising or denoising function, right? You basically start with the image, you noise you introduce noise into the image and completely sort of generate the noise out of it and learn that noising function. Then you start with noise, complete white noise, and start injecting that, denoising it using the same function to generate something meaningful, right? But the probability function and the schedule used to do that will essentially match the text given to you. For example, please draw a castle for me, and so this is what will happen. You start with white noise, a probability function is applied which can generate a castle. Every iteration you start denoising it using a certain probability function and the schedule, and eventually you see something which looks like a castle. That's exactly how the process works, right? So just to summarize in this one, the reason why I wanted to go a little bit deeper into this was two things. One is, please remember they're probabilistic models, number one. And what I mean by that is that's the reason the language models, the term used now is they will hallucinate. You heard that term before? That they can give you wrong answers perfectly confidently, like a bad student sitting at the back bench and bullshitting to glory, right? That's exactly how these models work. Is it a bug? No. It's a feature of these models because they're probabilistic models. Now, if you're training it on a set of data, it's a large latency space they've trained on. It's a large model. So large model has trained a large latent space. Some space will be very, very dense. Some spaces will be very sparse, where it hasn't seen enough training data. So when if you're asking a question which is in that sparse area, it will generate something with a low probability. But since it is generating something, the best number is a 20% probability, it is most likely going to hallucinate in that area. But in the areas which are dense, in which it has seen enough examples, it will generate something with a 90%, 99% probability, and hence will be very interesting, answers will be very appropriate, and you will love, and that's the reason you love using some of these large language models. So that's one important element. When you're dealing with these large language models, you'll have to deal with hallucination. You cannot wish it away. That's one. Other piece is that because of the largeness of the models, they are exhibiting a behavior called very good few shot or a one shot or few shot learners. That's a little technical term. Now, what do I mean by that? See, typically humans, kids, when they're learning, we show it to them. Hey, this is a remote. One kind of a remote. I'll show another kind of a remote. You give him 3 examples. Next thing you ask the kid, what is this? He'll say it's a remote, right? And that's exactly what a few-shot learning is. And these models start exhibiting very good few-shot learning behaviors. That means if you can show 3, 4 examples on a particular task, they start performing very well after that in that task, right? And that's exactly what. So that's a very important, result of these property of these models. They're very good few-shot or one-shot learners. So those are things to be sort of just hold on to that, and that's what you'll use some of that later. I like this slide a lot. This is just a comparison in typically the traditional AI/ML. How would you do it? Traditional AI/ML, you will get data. You'll do supervised learning. You label the data. That's what you see on the left. You take the data for every problem you're solving. You're labeling the data for that problem. You're building a model for that, solving that problem. Text generation, summarization, or whatever that is. But in the new world today, with the foundation models or the large language models of sorts, you essentially have unlabeled data. We talked about the autoregressive nature of these models. That means you already have a corpus which has the next word prediction there already built in, so you don't have to label the data. Using unlabeled data, you create what's called the foundation model, large model. Yes, it's expensive to train that model. Any guesses how much it's going to cost you using a GPU or a high-end compute to train a model of 100 billion or 200 billion parameters, one round? It's in millions of dollars. Just the compute cost of training it is like $3 to $7 million on a single run on a maybe 100, 200 billion parameter model, right? It's expensive, not everybody can do it. But if somebody's done it and that model is available to you, now you can fine tune it for the specific applications you want to. So single model, foundation model trained once, pre-trained as they call it, you fine tune that for different tasks. And that's the paradigm shift which LLMs have introduced now. I'll pause here. Any questions? Is the pace is reasonable, or should I speed up, or should I slow down, or should I just? Is it okay? Okay, so coming to what kind of foundation models, we've seen LLMs are text-to-text models. You gave a text, it's generated text. There are, text-to-image models, the stability models, which we've seen a little bit. Then there is something called text-to-embeddings, and hold on to that. Embeddings are essentially the numeric representation of the sentences you're giving, and that's the multidimensional attention you talked about. It's a vector representation of what the sentence conveys. Hold on to that thought. We'll talk about a little bit more on the embeddings, how they're useful. So why are they successful today, these models? 3 reasons, and I've covered all of it. I'll summarize that. Number 1 is the transformer architecture. That's a wonderful architecture. It started off for being able to represent language semantics very, very well, but it is now also being used for other applications. For example, new GPT has come in, which is for time series. Who would have imagined that a language model, the foundations of a language model are now also being used for predicting time series? Now what happens is these tokens, instead of the words or the word relationships, become events. And you have hypothesized some attributes of the images, you can start building transformer model and start building and predicting based on the same architecture. So that's powerful architecture. Other pieces in context learning, which I mentioned about the zero shot. Zero shot means out of the box. I didn't mention that earlier. But one shot is when one example, or few shot is few examples given. It learns to perform on the task using those examples. Then what I like the most is about the emergent behaviors at scale. That's a very powerful, very loaded term. What that means is when there's 2 things. One is the size of corpus you're training, it goes big, multi-billion lines of corpus from Wikipedia, and also the fact that models are big with multi-billion parameters, 200, 300 billion parameters. The moment that happens, they start exhibiting behavior which even surprised the original developers. So that's what we're seeing with LLMs. When the LLMs were trained with that level of magnitude, they started exhibiting behaviors like, why does it happen? They're good at few-shot learning. It's very unintuitive, because in a typical traditional AI/ML sort of a world, we require a statistically significant data sample to train and get reasonable results out of it. But here, because it's already pre-trained on a large amount of data, only 3 or 4 handful of examples, it starts learning. And that's a very surprising behavior. Mathematically, I don't think any of us expected that, but it started behaving, and consistently, the papers written around that, it's consistent, there is a mathematical foundation, we built on that now. Originally, when it started exhibiting their behavior, even the original developers of these LLMs were surprised why they're doing it, right? Now, in retrospect, they're building some mathematical foundation, but the fact of the matter is a very good, and new behavior at scale is emerging, and that's why they're successful. And that's the reason they're here to stay. It is not like any other hype you've seen before, like a Web3 or any of the things, right? Or maybe the earlier sort of winters which AI has gone through. This stuff is here to stay. There might be some element of hype, but this stuff is here to stay for a long time and impact every industry, every area you're working on today. Now, I just want to also highlight the fact that another important element when you're building anything around or large language models and stuff is about what's called reinforcement learning with human feedback. And what that means is that, as I said, they will hallucinate, right? The models will hallucinate. But how do you build something? This is an important element called, see, this is a meme I picked up. It's a meme that I'm sort of a little older than most people, and the new generation is all about memes these days. So I decided to pick up a meme from the internet. So this part of the meme essentially is where the unsupervised, that auto-regressive learning has taken place. That's the pre-training part, where the models are pre-trained. Now you're picking up, you see some of the models when using it, they'll say thumbs up, thumbs down, answer was right, answer was wrong, whatever. And that's the reinforcement learning feedback. So based upon that, you take that feedback, validate that feedback, and do basically a supervised learning to improve the models. So unless you have that loop, you sort of you need to have that loop when you're building that anything with LLMs. That's a very important element of any LLM-based system. I'll just highlight the prompts now. This is interesting, you picked this word called prompt engineering. I was doing a keynote in Seoul in May, or in June actually, and just before my session, there was a lady invited, and the topic of the conversation was prompt engineering, a new discipline. This lady said, I'm a prompt engineer, and she spent 30 minutes there on the stage with 1,000 people in the audience, explaining why a prompt engineering is one of the most important sort of new roles which is emerging in the industry today. Right? Whether you believe it or not, it's up to you, but this is something for real. I mean, how do you prompt a large language model to get the response you want? Right? And I've seen prompts, and now with the context size of the tokens input into a language model becoming very big now. Earlier it was very, every new model release, like a new model from Anthropic, which is basically Claude 2, has I think a 80K limit. It's a huge, you can have pages of text given to it as input, right? The limit sort of getting really, really expanded now. Now with that, the prompt engineering becomes even more important. Well, how do you put a prompt? This stuff which you mentioned about zero-shot learning, how do you give the examples within the prompt? These are in-context learning. That means you give these examples in the prompt for it to prompt and give you the results the right way. So that whole idea about how you prompt is becoming a very important discipline. It's no longer, it's becoming an art rather than a science, right? So what kind of prompts exist? So one is, of course, a zero-shot prompt, which basically you just say something and it returns back with something. Oh, that's it we have? Oh, okay. Okay. And then, of course, you have, other pieces, basically a few short prompt, where you essentially embed your examples in there, and then it generates a response. Other interesting ones are the role-based prompting. I say I'm a software engineer, or I say I'm a hardware engineer, I'm a financial analyst, how would I respond? So LLMs start behaving that way. The other is a role, called the the chain of thought prompting, because they're not good at logic, LLMs are not good at understanding and reasoning, right? So can I give an example of how do I arrive at an answer, step 1, step 2, step 3, and they start learning from there. Again, a manifestation of a few shot learning. So anyways, I'll just skip these examples of these things. Then there's a concept of training. This is an important element that you essentially, one of the things which is happening in the industry is that, the language models, they work the best if you train it on your own data, if you fine-tune it on your own data. So you have a specific problem at hand, you basically take the data and fine-tune for your own niche task. So some of the research is suggesting that instead of a large model which can solve for everything, which can answer questions about football, cricket, weather and everything else, smaller models which are fine-tuned on your own niche in application start performing better, and they're better even at cost economics. When large models means to train them and to deploy them and inference from them will cost larger amount of money, but a smaller model when inferencing will be much better on unit economics, right? So that's another trend which we are seeing, that prompt tuning, the fine-tuning the models, smaller models for a specific task would essentially, this is the one, Stanford and Alpaca experiment pointed to that. Take a smaller model, instruction fine-tune it for niche applications, they start performing better. So anyways, with that, idea is that, how do you manage hallucination? The key issues are hallucination. So this is the mechanism of it's very interesting use case, how hallucination is addressed. That you essentially have your own corpus of PDFs, for example. Like use case is an insurance company have thousands of insurance policies. Now you want the question and answer to happen, use LLMs, using the text in the policies. Now you essentially would take the customer data, which is these policies, thousands of policies, you use all of what's called LLM embeddings. That means your semantic interpretation, and you put into a vector database. Now the question when you user ask, you also embed them and now do find a match. You can get whatever that section of the policies which appropriately answers the question, and then feed it to LLM. Hey, Mr. LLM, this is the question I want you to answer from this corpus. So you're now minimizing hallucination. And you're also tell the LLM that if you don't get the answer in this corpus, say I don't know. So you're essentially minimizing hallucination. You can trace back on what basis the LLM has answered you. So this is the technique very widely being used now for various applications. So this is just, let me just quickly move forward on because of interest of time in terms of moving about, the use cases. As I said, it encompasses everything, from a text generation to the code generation. Amazon has Amazon Code Whisperer, which is aid for software developers to write code. Now, we have seen 57% improvement in productivity of software developers because you write a comment, it generates a code for you, right? Similarly, on the side of images, image generation, text, video generation, we've talked a lot on that. The 3D animation generation, healthcare. In the morning we had a panel. The healthcare stuff around drug research, new candidates for drugs, generated by generative AI, the protein folding, all of the stuff is happening. And most importantly, synthetic data. Now, even if you have radiology images where you have a software or a computer vision software which is diagnosing from the radiology images, now augmenting that using synthetic data generator using generative AI improves those algorithms and improves the efficiency of diagnosis. So amazing. Across the board, you'll see productivity improvements ushered in generative AI space. In terms of Amazon's stack, we essentially have 100,000 users already on AIML. We have in the DNA, we have the DNA of AI, the stuff which you did on recommendation engines on Amazon.com, Amazon.in, the stuff which you do with the warehouses, stuff which we do with Alexas. We've been doing it for decades now. And essentially, our focus has been democratizing. If you look, this is the stack which looks like on AWS. The bottom layer is essentially the hardware layer and where we have a highest variety of different computes available because compute is important to train and deploy these models. We have our own silicon, which even gives you better ROI on cost performance ratio on Inferentia and Trainium. Train your models, Inferentia to deploy your models. That's our own custom silicon. We have the middle layer, which is the SageMaker, which allows you to build and deploy the pipelines and even monitor them. Monitoring is important too. The whole end-to-end monitoring means that is the model drifting, is the model has a bias, all that stuff is available in the middle layer. Top layer is the end applications like Code Whisperer, we have announced Bedrock, which is an API availability of on top of multiple models, generative AI models. So I'll just skip this slide and. Just to summarize, in this slide, if you're a model builder developing language models from scratch, foundation models from scratch, the stuff around, the SageMaker, which is the bottom layer, and the underlying hardware layer, which has the clusters of data centers where we can deploy and build your models. The libraries available to parallelize the models, efficiently train your models are very, very impressive, very, very interesting. Your model parallelism, data parallelism, all the stuff with feature is supported. So model builders like Stability, like Anthropic have built on AWS. That's if you're a model builder. If you're a developer who's using existing models to fine tune, the SageMaker Jumpstart provides access to multiple models and also Bedrock, which is in API access. SageMaker Jumpstart is an access where you essentially have access to notebooks, more technical. You have more control on your own instances where you deploy these models, whereas the Bedrock is a version where you get serverless. You get an API access to the same models. Right, in terms of an additional model, we also announced our own Titan model, which is again the most state-of-the-art models on Delhi language models called Titan. But the idea is to, and at the bottom layer, as I said, is the infrastructure layer, the widest variety of compute available, including our own custom silicon in Inferentia and Trainium. I'll just quickly go through few more slides. So here is a look at the democratization of the models. On the left side, you see the models which are publicly available. Open source models, the Falcons, the Llama 2, the Open Llama, they're all available on SageMaker Jumpstart at a push of a button. You go there are samples, playground available, you can play around this model, see what response you're getting, and say, okay, here is the model I want to deploy, click it, the model gets deployed on your instance. Very easy to start playing around. And that's the amount of variety of models available to you are huge. And then the private models, where you can license from third party, like a Cohere models, AI21, Anthropic. You can actually license the third party models also from within the SageMaker Jumpstart and also Bedrock. As I said, the difference between SageMaker Jumpstart and Bedrock is SageMaker Jumpstart allows you more control in terms of deploying models on your own instances. You manage your own instance. Bedrock is a serverless API-based access to all these models. Let me give one more. So here is an example of why it is important to have very custom your instance for where to deploy your model, because it impacts your cost, training costs as well as inferencing costs. So right choosing of instance is very important, and a variety there is very important. I'm going to highlight again the Inferentia and Trainium. We have 50% better price performance if you use Inferentia and Trainium for deploying the same model on the hardware. So I'll just quickly go through this slides fast enough, and let me. Instead of time, I'll just go through it, and a few more slides to go. Okay. So these are all about more detailing in terms of how we can. So why build on AWS? One is, of course, the flexibility, that the amount of models available for you to choose from is fully democratized. So you have, and again, our belief is that it is not just about one model. When you deploy production applications, you may require multiple models for different things. For a single problem, you may use model 1 for solving one subpart of the problem, model 2 for solving subpart 2 of the problem, and so on and so on. So ability to have access to these models at one go is important. Secure customization. When you're customizing, people question, if I put my data to fine-tune, where my data goes? Is it secure enough? So we are allowing customization on your own VPC. When you push your data, please customize the model and fine-tune the model. It's your own VPC, so it's very secure. The most cost-effective infrastructure, the variety of hardware available downstream, and our own Inferentia and Trainium, 50% lesser cost in training the same model, or deploying the same model. And the whole SageMaker is sort of a platform from end-to-end building pipelines, from model training to deploying and monitoring for bias and drift. And the end solutions, whether it's called Whisperer or the top layer, which you saw in terms of the applications from speech, text, video, all of them are available as an API on the top level. So again, that's basically, these are just a summary of the models available in Bedrock or Amazon's own models called Titan, AI21 Jurassic models, very good at multilingual support. Anthropic are very, very powerful models with a very high level of input, very high limit on the input, token stream at the input. And stability is the video model, the image generation models. So with that, I'll sort of come to the end of my presentation, so summarize. These are some, I like this slide a lot. 2025, we expect more than 30% of new molecules or drugs to be discovered using generative AI. 2025, 30% of outgoing marketing messages would be synthetically generated. And by 2030, a major blockbuster film will be made with 90% content synthetically generated using generative AI. So best of AI/ML start of the building on us. So start your journey and on AI/ML or generative AI on AWS. I'll stop here for questions, and maybe running a little late, maybe one or two questions if you have, we can.
We have time for questions. That's why I mentioned.
Yeah.
We have 5 minutes for questions if there are questions.
Sorry?
Specifically for the legal tech industry, where the laws and regulations keep changing, what is your thoughts, specifically in terms of using ChatGPT 3.5 versus any of the AWS models?
Yeah, so I will not comment on specific competition names or whatever, but I will definitely talk about specific to LLMs. Now, I believe that off-the-shelf LLMs need to be fine-tuned for every niche application like a legal. So there are companies who are building a layer on top of fine-tuning the existing models across multiple open source as other models to build the legal layer on top of that, right? Now, in terms of your question about fast changing legalities and the previous cases and everything, it's an ongoing build which happens, right? That's a, and you have to continuously upgrade your models. But that's a layer needed, fine tuning, and the very good use case of LLMs is a legal use case. There are many companies I know building LLM-based legal recommendations based on previous cases, based upon the laws itself, and so on, right? And I know company, one of the startups in Korea, I know a few startups in India doing that already. But you have to keep pace with the changing. New cases have to keep updating. You have to keep updating new cases into the system. Yeah. Yes, please.
So, sir, you said reason for hallucination. You linked it with the probabilistic model of the traditional ML models, right?
Can you be a little louder? Sorry, I'm not able. Sorry about that.
Hello.
Yeah, it's better now.
So you related the hallucination, the problem of hallucination, with the traditional ML problem, right? That they are probabilistic models. So for the last 20 to 30 years, they are being already trained, right? So the present model that we are using for example, for GPT, right? So it's already pre-trained over the past 20 to 30 years. So why the hallucination, apart from the prompt part, right? The prompt part is new because it's learning every day regarding the prompt. But the results should already be trained for the past 20 to 30 years. No?
Well, you sort of, yeah, a good question in a way, but I think you're confusing two things. The traditional AI ML models are not generative models, number one, right? They're only giving you certain, regression algorithms or certain probability of detection of whether this is the remote or whatever it is, right? Those are only classification or regression problems. They're not generative. Now, when you're generating from you're randomly generating that content, right? And random generation is, and again, I'm emphasizing the APIs which have been introduced are called, completion APIs, right? Which means that your prompt is not really a question for an LLM. Your prompt actually is a starting point to complete what you started to write, right? So that is the prompt engineering becomes very important. So when you build something, it has seen similar starting points before, it will complete it with a higher level of accuracy, at 99% accuracy of the next word prediction and the next word prediction and the next word prediction, right? But if it's not seen enough samples, you will be in a space, in that latent space, which is very sparsely populated, and it hasn't seen enough examples. So it will start generating something at a 20% probability, which could be completely junk, completely rubbish. So that's sort of the point why when you're generating the random nature of these models, because it's random sampling. It actually is truly random sampling following a probability distribution. Now, if the probability distribution is not strong, you will see something which is going to be rubbish. That's sort of where the whole idea of hallucination comes in, right? And however data you use to train, idea is that if it has enough data in that space, if it is a dense space in the latent space, you will see good answers because the probability would be at 99%, 92%, 90%. But there will be spaces, there are large models, you can ask a question on around an area or the starting point where it hasn't seen enough data earlier during training. So it will hallucinate. That's the point I was making. Yes, sir.
I think last question.
On Indian languages, I mean, we've got this recent report that Hindi is the only, Hindi is 39th, Hindi script is 39th out of the top 50 languages on the internet. So clearly we have insufficient content, right? And it used to be somewhere around 14, 15, it's dropped to 39th. All Tamil and the other languages, all the other scripts are beyond 50. Now, if the content itself is not there, how useful is generative AI for Indian scripts? Because we're seeing gender issues. It confuses male, female, on even Hindi. So Hindi being the largest in terms of Indian script content, it's still, so isn't there, when we are looking at statistical models, where is that turning point? Because we are a laggard in content creation, meaningful content creation on Indian scripts. Yeah. So for India, non-English languages, how useful is this and who's working on this? I mean, is there a way to address this gap?
No, absolutely, that's a fantastic question. You're absolutely right. The amount of data is insufficient. The model accuracy would not be up to the mark, right? You're absolutely right. And that is the reason there is a push. I know the AI for Bharat Lab, founded by Nandan Nilekani in IT Chennai, they are at the forefront of doing that. Ministry of IT through the Bhashani project have been able to push a lot of data collection. They have last 6-7 years, even before the LLMs came, they've been building on this data corpus. They have crowdsourced the data Even PM in Man Ki Baat announced that Bhasha Dan Kijiye. If you know any language, please speak a few clips and send it to us. There are a lot of data they've collected. Now, is it sufficient? It is sufficient, but at least there are 22 languages in Indian Constitution. I think for 16, they seem to have reasonable data they've collected using All India radio recordings, do some transcriptions, do synthetic data generation. They have reasonably good data on 16 languages or 22 Indian languages, is what I understand. And they're building this up at AI for Bharat Lab in terms of building these LLM models. Please understand the stuff on Indian languages, the tokenization is different. And that's a problem. In the current set of models where they're using any of the GPT models, they're using standard tokenization. So they're at a word level. When you're doing any Hindi or English or Tamil there, it is at a word level, not at a token level. So for doing it from scratch, and that project is on building a LLM for Indic languages from scratch, would have to have local tokenizers, which will work at a token level, not at a word level, right? And that's a charter which is on. I think there is also a startup which is founded, which is focusing only on building these LLM models. So I'll not be able to divulge more than that, but I understand there's a startup which is now working, and it's well funded now by the VCs, who's working on building around LLMs for Indic languages.
I think Anurag is available probably after the session. So thank you, Anurag, for giving us our insights. Let's have a round of applause. Please stay. Please stay. That was a very interesting session, and people who've been following since morning, how we have been decoding the AI and generative AI, and of course, learning what are the different options, how we can really practically use it. So we wish to present Anurag with a token of appreciation from TAI. Thank you our speaker gift partners, Lenscard, the Good Glam Group, Sirona Hygiene, Yukta Media for these wonderful speaker gifts. So our next session, it's also a masterclass